Hello, today I'm going to talk about quantum algorithms for research. This is a fast abstract, so I'm going to be reporting on ongoing research. So let me go to my slides, and I hope you enjoy the talk. Okay, let me just start by trying to motivate you towards studying quantum algorithms for research.
Now, research algorithms play a crucial role in many applications, particularly in artificial intelligence. So, research algorithms appear in many different domains: game-playing systems, production systems, robotics, optimal planning, as it is called. And so, in the language of artificial intelligence, an agent performs reasoning by exploiting some knowledge or some previous knowledge about a given problem. And so, research consists of one such form of reasoning. Now, at the bottom, you see a simple binary tree search, and at the bottom right, you could see a different tree search algorithm. It is called Monte Carlo tree search algorithm, and it is widely used in reinforcement learning applications. Now, what about Q motivation, the quantum motivation? We all know that Grover's algorithm can give us a quadratic speedup in searching unstructured databases, and so if we could map quantum search techniques, Grover's algorithm and all of its variants, into a quantum tree search technique, maybe we could enhance some of the tree search algorithms. Now, another interesting topic is amplitude amplification. Amplitude amplification is some form of a quantum heuristic, and so at this point, I will leave you with a question that I find very interesting, which is, what about quantum informed research? Maybe amplitude amplification has something to do with this. Now, at the end of this talk, I will try to answer this question. Okay. Now, the rest of the talk will be as follows. Firstly, I will briefly talk about classical tree search algorithms. Then I will talk about the state-of-the-art of quantum tree search, and then I will report on ongoing investigation about generalizing quantum tree search, and I will clarify what I mean by generalized. Now, at the end of the talk, I will refer to some new ideas that we've been working on, and maybe we could discuss them afterward. Okay, let's start by classical tree search then. Now, in tree search, the goal is to find a sequence of actions that lead to a goal state. So we start in a given node, and we have a goal state that we want to reach, and so we need to find the optimal sequence of actions. Now, given that we don't know anything about the structure of this tree, in the most general form, the complexity will be the branching factor B to the depth of the tree, D. So at this point, another interesting question arises, which is, what happens when we have a tree with non-constant branching factor? Okay, when we have non-constant branching factor trees, using the maximum branching factor no longer makes sense, right? And so in these cases, we should use the effective branching factor. It's known that the effective branching factor converges to the average branching factor. And so in these cases, the complexity of finding a goal state is the average branching factor exponential with the depth of the tree. Now, at this point, another question arises, which is, can we do better than brute force search? So can we exploit some knowledge to find a goal state in less time? And this leads us to informed research. Now, in informed research, we exploit previous knowledge from the problem, some given knowledge about the problem, and we expand the nodes that verify some criteria. Now, we use some heuristic function g of n, and so for example, for the traveling salesman problem, g of n could be the distance to destination. So in informed research, we prioritize over what nodes we expand. And so for the case of traveling salesman problem, we expand the node that is closer to the goal state. Now, in quantum research, the main difference is that the agent now has the ability to perform actions in superposition. And so what we need to do is to map an action into a quantum state. For the tree in the left, we see that we have a branching factor of 2, and so the quantum state that represents an action for the first level of the tree can be represented by the uniform superposition over action 0 and 1. Now, the quantum state A0 represents the uniform superposition over all possible actions to take at level 1 of the tree, but in general, we want to be able to run over all possible paths of the tree, and so we can add multiple quantum registers for different actions, and so we can build the quantum state A that will be the tensor product between all possible actions. Now, at this point, to discover the optimal sequence of action to reach the goal state, we're basically in the same paradigm as in the original Grover's algorithm. And so we just need to have an oracle that is able to mark that correct sequence of actions. And so now the goal is to reach the goal state. Now, the goal is to amplify the amplitude of that correct sequence of actions, so the sequence of actions that lead to goal state. And so all we need is an oracle that signs that correct sequence of action.
Okay, again, our oracle will invert the phase of the sequence of actions that lead to the goal state. Now, we build the uniform superposition over all possible sequence of actions until a depth d, which means that each sequence of actions will have a corresponding amplitude, which will be 1 over the square root of a to the d. Now, we can look at the quantum state A, the uniform superposition over all possible actions, as being spanned by the subspace of good actions, which means the correct sequence of actions, and being spanned by the subspace of bad actions, all over possible sequence of actions. So, following Grover's algorithm, we know that applying j iterations, the amplitude of the correct sequence of actions will be amplified. So, now the goal here is to find the optimal number of iterations. We know that theta is the arcsine of 1 over the square root of a to the d. And so if we solve for j, we can see that we need the square root of a to the d iterations in order to reach the optimal sequence of actions. And so the square root gives us a quadratic speedup compared to the classic counterpart. Now, an interesting question arises, which is what happens when we have non-constant branching factor trees. When we have non-constant branching factor trees, we know that the effective branching factor converges to the average branching factor. However, in the quantum setting, we cannot use the average branching factor. We must use the maximum branching factor always, because we don't have a way of distinguish what action should we take at what state. And it turns out that Grover's algorithm can no longer guarantee a quadratic speedup in all cases. Specifically, when the average branching factor is greater than half of the number of superposition terms, then Grover's algorithm provides a speedup, and in the opposite direction, Grover's algorithm can no longer provide a speedup. Now, let's talk about generalizing quantum research. Now, by generalizing, we mean that we need to use Grover's algorithm to provide a speedup for all non-constant branching factor trees. Now, the solution to deal with all possible non-constant branching factor trees lies in, instead of representing only actions, we can represent the node as well. So instead of using the quantum state A, which is the tensor product of all possible sequence of actions, we could have the state psi, which is the tensor product between the node and the sequence of actions. And this allows us to create a superposition over the set of admissible actions to a given node, instead of just creating a superposition over all possible actions. Now, how can we create the superposition over the set of admissible actions to a given node? Now, let A sub s be the subset of admissible actions to a state S. We can see in the tree in the left that for the node S0, we have that admissible actions are A0 and A1. And so we can build a quantum operator A that receives the current node and an action register initializing the ground state, and maps that action register to the uniform superposition over the set of admissible actions conditioned on the current node. Now, once we have a quantum operator that prepares the superposition over the edges of the tree, we need a new operator S that acts as a state transition operator. So this quantum operator S will guarantee that when we receive a state action pair, we can map the state to the correct next state S prime. And so, interleaving A and S for a depth d, we can create a superposition over all paths until depth d. And now we just play the same game as before, right? Just need to build an oracle that inverts the phase of the quantum state that has the correct goal state, and then apply j iterations of the Grover's algorithm in order to amplify the amplitude of sequence of actions that lead to the goal state. And once we solve for j, we find that we need the square root of the average branching factor to the d in order to reach the optimal sequence of actions that lead to the goal state. And so, this way, we have a quantum algorithm that solves quadratically faster for the optimal sequence of actions in any type of branching factor tree. Now, there are downsides, of course. So, the first downside is that we need to double the number of qubits needed compared to the first quantum approach. And the second one is that the quantum operators, A and S, are controlled operations. And so this means that the number of gates will increase exponentially in the number of qubits, and this could lead to a poor performance, at least in the current state of the art of quantum computers. Now, to end this talk, let's give some new insights on quantum-informed research. Now, in the beginning of this talk, we said that amplitude amplification is a form of a quantum heuristic. And so, consider the interesting case of Grover's algorithm when we have n/4 marked elements. In this case, Grover's algorithm needs a single iteration to read a marked element with certainty. And so, consider the following example. If we had 4 actions, and so we build the uniform superposition over 2 qubits, and if we want to collapse this state into the action 1, 0, Grover's algorithm needs a single iteration to read this state with certainty. And with this, we have 2 interpretations. First, this could be interpreted as performing pruning. And a more interesting point is that now we could use an oracle that marks an action that has the highest score following some metric, and this could be some quantum greedy best first approach. Now, this technique only works for the case when we have a such space of n elements and we have n/4 marked elements. Now the question is, how can we generalize this to an arbitrary such space and an arbitrary number of marked states? First of all, we could use an oracle to select 25% of the entire such space based on some metric, and then use a single Grover iteration, collapse the quantum state, and see if we reach the optimal sequence of actions that lead to the goal state. Or we could apply exponential search instead. And more interesting, we could perform the same thing again. So we could recursively select 25% of the search space, and maybe this will give a recursive quantum search algorithm. With this, I finished my talk, and let the discussion begin. Thank you very much for your attention.